So let's take a look at an example. Let's let W be the subspace of R3 with orthogonal basis given right here. And let's let X be some vector in R3. Let's compute the orthogonal projection of X onto vector space W. Okay. So how do we do that? Well, we know we have an orthogonal basis here, right? And because of that, to compute the projection of X onto vector space W, we just need to compute the projection of vector X onto each vector in the orthogonal basis. So I just want to compute the projection of vector X onto, let's give these names, let's call these V1 and V2. So projection of that vector X onto V1, the projection of vector X onto V2, and then you add all those projections together, okay? Now, the formula for a vector projection, you take the dot product of X and V1 divided by the norm of V1 squared multiplied by vector V1, and then do the same thing for this one. So X dot V2 over norm of V2 squared times vector V2. So I'm just using the formula for the orthogonal projection of one vector onto another, okay? And now it's straightforward. We're just taking the dot product. We are taking the norm and such, so on. So dot product of X and V1, 0, 3, negative 2, dotted with negative 2, 1, negative 2. I get 0 plus 3 plus 4, I get 7. Over norm of V1 squared. So that's 4 plus 1 plus 4, that's 9 times vector V1. Plus, and now do the same thing for X and V2. So dot product of X and V2. If I take the dot product of these, I get 0 plus negative 6 plus 2. That's going to be negative 4. Over norm of V2, that's square root of 0 plus 4 plus 1, which is square root of 5. Squared is just 5. Times vector V2, which is 0, negative 2, 1. Negative 1. Okay? If I'm going to add these together, I'm going to need a common denominator, right? So let's get a common denominator. Unfortunately, the smallest I could go is 45. Okay? So that's 35 over 45 times negative 2, 1, negative 2, plus negative 36 over 45 times 0, negative 2, negative 1. So if I actually multiply the scalars in, I get negative 70 over 45, 35 over 45, negative 70 over 45. For my first vector, I just did the scalar multiplication, 35 over 45 times this vector. And then do the same thing here. I'm going to leave the negative on the outside here. Actually, maybe I won't because these are both negative, so I'll multiply the negative in there. 0 times anything, 0. Negative 2 times negative 36 over 45 is positive 72 over 45. And then negative 36 over 45 times negative 1 is positive 36 over 45. All right, we're almost done. Let's add them together. My first component, negative 70 over 45 plus 0 is negative 70 over 45. My second component, 35 over 45 plus 72 over 45 is going to be 107 over 45. And negative 7 over 45 plus 36 over 45 is going to be negative 34 over 45. That is the orthogonal projection of vector x onto subspace W. Okay. Now this is in three-dimensional space, so we can actually see a visualization of what this looks like. So let me pull up Desmos and we can see a picture. Pull it over. Okay, so I've got three-dimensional space here. Now, my two vectors, the two orthogonal basis vectors, are v1, v2. Notice that they really are orthogonal. If you look at them directly head on, they really are two orthogonal vectors. So that's my orthogonal basis. Because it's two vectors, the space that they span is a plane. They are an orthogonal basis for a plane. That's my vector space W. Okay. Now, the vector I'm interested in here is this one right here. I want to find the projection of this vector onto the plane. That's what I'm going for. And so after doing all that work, the vector I found is this vector. Notice it is in the plane, and that is the orthogonal projection of vector x onto the subspace W. And you could see if I drop the perpendicular, it is perpendicular to the plane. Okay, so that's what we found. The piece of my vector x that was in subspace W.